November 16th, 2022. Kennedy Space Center, Florida. Launch Complex 39B. The most powerful rocket in 50 years is standing on the pad, 322 feet tall, 5.7 million pounds, ready to launch. Inside the spacecraft, at the top, 4 seats, life support systems, oxygen generators, water storage, food supplies for 3 weeks, windows with a view of Earth and the Moon, and nobody on board. This is the most advanced spacecraft ever built for humans. Designed to carry 4 people beyond the Moon and back. Every system tested on the ground, every detail perfected, every contingency planned for. And when it launched that morning, the crew cabin was empty. Tonight on Stardrift FM, the story of Artemis I, the mission that went farther than any human has ever been, with no humans aboard, 25.5 days, 270,000 miles from Earth, 161 tests, 2 moon flybys, a heat shield that came back cracked in over 100 places. What they learned, what they found, and why sending it empty was the smartest decision NASA ever made. This is Stardrift FM. Let's begin. November 16th, 2022, 6:47 and 44 seconds, Coordinated Universal Time, 1:47 in the morning, Eastern. The Space Launch System, SLS Block 1, ignites. 4 RS-25 engines at the base of the core stage, each one producing 512,000 pounds of thrust. That's 2.05 million pounds from the core stage alone. Then the solid rocket boosters light, 2 of them, 5 segments each booster producing 3.6 million pounds of thrust. Total thrust at liftoff, 8.8 million pounds. That's 15% more powerful than Saturn V, the rocket that took humans to the Moon in 1969, the most powerful rocket ever successfully flown until this moment. And nobody felt it. The boosters burn for about 2 minutes, 1.6 million pounds of solid fuel in each one. Polybutadiene acrylonitrile, PBAN. Burns fast, burns hot, at 2 minutes, booster separation. They fall away into the Atlantic Ocean, not recovered, unlike the Space Shuttle's boosters. These were one-time use. The core stage keeps burning. 730,000 gallons of supercool liquid oxygen and liquid hydrogen, feeding those 4 RS-25 engines. 8 minutes after liftoff, core stage shut down. The interim cryogenic propulsion stage, ICPS, takes over. 1 RL-10 engine, pushing Orion the rest of the way to orbit. 18 minutes after liftoff, the solar array wings deploy. 4 wings, 7 meters each. They unfold like petals. 49 square meters of gallium arsenide solar panels, generating 11.2 kilowatts of electricity. Orion is on its own now. The trans-lunar injection burn happens next. The ICPS fires one more time, pushing Orion out of Earth orbit and toward the Moon. Then it separates. Its job is done. Mike Serafin, Artemis I mission manager, said this after the mission. 7 feet per second, after 8 minutes of powered flight, after burning 730,000 gallons of fuel, after accelerating 5.7 million pounds of rocket and spacecraft to orbital velocity, remarkable precision, and nobody was inside to feel it. The spacecraft is called Orion. It's a capsule design, like Apollo, but larger. 16.5 feet in diameter, 26 feet long from the nose of the crew module to the bottom of the service module. Crew capacity, 4 astronauts for missions beyond low Earth orbit. Habitable volume, 316 to 380 cubic feet. That's about the size of 2 minivans, roughly 1.5 times larger than an Apollo command module. On this flight, 0 crew. The life support systems are running. Temperature is regulated, humidity controlled, carbon dioxide scrubbed from the air, oxygen generated, water stored in tanks. Everything a crew would need. But there's no crew to use it. The bottom half of the spacecraft is the European Service Module, built by Airbus Defence and Space in Bremen, Germany. Delivered to NASA at the end of 2018. This module does everything Orion needs to stay alive in space. It provides propulsion, electrical power, water, thermal control, atmosphere, It's a collaboration. Over 150 engineers from 10 countries worked on it. The European Space Agency's contribution to Artemis. 4 solar array wings, 7 meters each, generating 11.2 kilowatts. That's twice what Apollo's command and service module could manage. During the mission, those solar arrays provided 15% more power than projected. The panels tracked the sun, adjusted their angle in 2 directions, kept the spacecraft powered for 25.5 days. 33 engines on the service module, 3 types, 1 main engine and AJ-10-190. Refurbished from the Space Shuttle's orbital maneuvering system, 6,000 pounds of thrust. This engine handles the big burns. Orbit insertion, departure, return trajectory. 8 auxiliary thrusters. Raw 4D-11 engines. Descendants from the Apollo era. 24 reaction control system engines, custom designed by Airbus. Arranged in 6 pods of 4. These handle maneuvering and position control. All of them working perfectly. Firing on command, adjusting trajectory, maintaining attitude. And nobody was there to monitor it. The environmental control and life support systems were running, making the crew module habitable. Fault-tolerant design, less complex than previous NASA spacecraft, but just as reliable. 2 radiator loops on the service module, expelling heat from the electronics, from the propulsion system, from the batteries. An ammonia boiler for additional cooling. NASA turned it off mid-flight, then restarted it after splashdown, testing its capability, gathering data on how the system recovers. Temperature stayed regulated. System stayed cool. Nobody there to feel the comfortable 72 degrees Fahrenheit inside the crew module. On top of the crew module, the launch abort system, 44 feet tall, 3 solid rocket motors inside. The abort motor pulls the crew module away from danger. 5 seconds of burn time, 0 to 405 miles per hour in 2 seconds if activated on the pad. The attitude control motor steers and orients the capsule during an abort. The jettison motor separates the launch abort system from the crew module before parachute deployment. Response time, milliseconds. It can activate on the launch pad or during ascent. Guides the spacecraft to a safe trajectory. Clears the way for parachutes and a survivable landing. It's a safety system, designed to save lives in an emergency, and there were no lives on board to save. Howard Yu, Orion Program Manager, said this after the first week: every system validated, every subsystem nominal, every test passing, nobody there to see it. Flight Day 1, November 16th. After the Trans-lunar injection burn, Orion is on its way to the moon. 3 days to get there. Flight Day 6, November 21st, 12:57, Coordinated Universal Time, the first moon flyby. Orion passes within 81 miles of the lunar surface, close enough to see individual craters, close enough to map the terrain with the optical navigation camera. The outbound powered flyby burn executes. The main engine fires, adjusting trajectory, slinging Orion around the moon toward its distant retrograde orbit. The moon fills the windows, gray and tan and white. Ancient impact basins, mountain ranges, permanently shadowed craters at the poles, and nobody looked out the window. The cameras captured it, 24 cameras total, 8 on the SLS rocket, 16 on Orion, recording every angle, every moment. But nobody was there to press their face against the glass, to see the moon 81 miles below with their own eyes. Flight Day 10, November 25th, the distant retrograde orbit insertion burn. 1 minute and 16 seconds. Changed Orion's velocity by 247 miles per hour. Distance from the moon during the burn, about 57,000 miles. Orion enters DRO, distant retrograde orbit. Distant because it's far from the lunar surface. Averaging 43,000 miles out, as close as 62 miles, as far as 70,000 kilometers. Retrograde because it orbits opposite to the moon's orbit around Earth. The spacecraft moves one way, the moon moves the other. This orbit is extremely stable. It requires minimal fuel to maintain. Gravitational forces from Earth and moon balance out. Orion could stay here for months if it had to. NASA wanted it tested for 6 days. Validate the navigation models. Prove that future missions could use this orbit as a staging point. Flight Day 13, November 28, 2022. Orion reaches its maximum distance from Earth, 268,563 miles. The previous record, Apollo 13, April 15, 1970, 248,655 miles. Apollo 13 held that record for 52 years. Artemis, I broke it by almost 20,000 miles. The farthest a human-rated spacecraft has ever traveled from Earth, and nobody looked back. The solar array cameras took a selfie, Orion in the foreground, Earth setting behind the moon. The Earth set shot, like the famous Earthrise photo from Apollo 8, but in reverse. Earth looks small from that distance. A blue marble, atmosphere barely visible, continents and clouds and oceans, everything humanity has ever known, compressed into a disk you could cover with your thumb. Flight controllers in Houston watched the telemetry. Every data point streaming back across 270,000 miles of space. Signal delay about 1.4 seconds each way. Systems nominal. Trajectory on track. Power stable. Thermal control working. All test objectives progressing. Nobody in the spacecraft to look out the window and take it in. Flight Day 16, December 1st. The distant retrograde orbit departure burn. 1 minute, 45 seconds. Changed Orion's velocity by 454 feet per second. Orion leaves DRO. Begins the journey home. Flight Day 20, December 5th, 1643, Coordinated Universal Time. The second moon flyby. Return powered flyby. Distance 80 miles from the surface, slightly closer than the first flyby. The main engine fires, adjusting trajectory one last time, sending Orion on its final path toward Earth. The moon falls away behind the spacecraft, shrinking, fading into the distance. Sung! The cameras recorded it. The optical navigation camera captured close-ups. The solar array cameras filmed the moon receding, and nobody was there to say goodbye. Artemis Way wasn't just a flight, it was a validation mission. A comprehensive test of every system on the rocket and spacecraft. 161 test objectives, some planned before launch, some added mid-flight when engineers saw opportunities to gather more data. Propulsion, navigation, communications, thermal control, life support systems, reentry systems, operations and facilities, everything that would need to work for a crew, tested without a crew. Let's talk about what they were testing. Propulsion systems. Characterizing all 33 engines on the European service module, how they perform in a vacuum, how they respond to commands, how much fuel each burn consumes, the main engine, the 8 auxiliary thrusters, the 24 reaction control system engines. Thruster burns of 95 seconds, longer than any operational burn needs to be, but the extra time gives engineers more data, more insight into engine performance over time. Testing radiative heating on the solar array wings during engine firings. Do the exhaust plumes damage the panels? Does the heat affect power generation? Validating the service module's propulsive capabilities for all the major maneuvers. Outbound Powered Flyby. Distant retrograde orbit insertion. DRO departure, return powered flyby. Every burn executed within a few feet per second of the target velocity. Remarkable precision across hundreds of millions of miles. Navigation systems. Exercising the entire navigation system over the full mission duration, from pre-launch alignment to post-landing recovery. Orion navigates using star trackers, inertial measurement units, GPS when in Earth orbit, and the optical navigation camera when near the moon. The optical camera captures images of craters during the close flybys, matches them to maps, calculates position and velocity. No ground tracking needed. Autonomous navigation, validating accuracy in distant retrograde orbit, where GPS doesn't reach, where ground tracking stations can't always see the spacecraft, where Orion has to know where it is on its own. Mike Serafin, mission manager, gave the mission an A+ after the first week. The navigation system's final performance, 7 feet per second off the target velocity after 8 minutes of powered flight. 7 feet per second, out of 25,000 miles per hour, and nobody was at the controls. Communication systems uplinked large data files to test reception time. How long does it take to send a multi-gigabyte file across 270,000 miles? Verified uplink and downlink capability sufficient for human rating. Can mission control send commands reliably? Can the spacecraft send back telemetry, video, and voice? Tested the SARSAT beacon, the Search and Rescue Satellite-Aided Tracking System. This is the emergency beacon that would alert ground stations if a crew needed rescue after landing. They verified it works. They verified the signal reaches satellites. They verified it doesn't interfere with recovery operations communications. End-to-end communication validation across 250,000 miles with signal delays over a second each way. Nobody on the other end of the radio to hear mission can control. Thermal control. Testing the ammonia boiler, the system that provides additional cooling when the radiators aren't enough. They turned it off mid-flight, then restarted it after splashdown, proving the system can recover, proving it can be shut down and brought back online if needed. Testing both radiator loops on the service module. How well do they expel heat? Can mission control adjust radiator pump speed and flow rate remotely? On flight day 14, NASA added a new test objective, thermal characterization of Orion, gathering more data on how heat moves through the spacecraft, how components heat up and cool down over time. Temperature stayed regulated throughout the mission. Electronics stayed cool, batteries stayed within operating range. Systems ready for a crew, with no crew to keep comfortable. Life support systems, environmental control systems, oxygen generation, water storage, atmosphere maintenance, carbon dioxide removal, everything working as designed. Temperature regulated to 72 degrees Fahrenheit. Humidity controlled, air quality nominal. The crew module could have supported 4 people for 3 weeks, maybe longer, but the crew module could have supported 4 people for 3 weeks, maybe longer, but the crew cabin was empty. Radiation data. 3 mannequins flew on Artemis I, Commander Munikin Campos, named after Arturo Campos, an electrical engineer from the Apollo era. The man who helped figure out how to bring Apollo 13 home after the explosion. Munikin wore the Orion crew survival system suit, the orange pressure suit astronauts will wear during launch and re-entry. Seated in the commander's seat, strapped in, Helga and Zohar, twin phantom torsos, made of materials that mimic human soft tissue, organs, and bones. Over 5,600 sensors and 34 radiation detectors embedded throughout. Helga wore no protection. Zohar wore the astral radiation vest, a garment designed to shield vital organs from space radiation. Measuring deep space radiation exposure, validating what a crew would experience beyond Earth's magnetic field, beyond the protection of the Van Allen belts. The data came back. Artemis I proved that radiation levels would be within safe limits for the crew. The AstroRad vest reduced exposure to organs by some amount, still being analyzed. But the key finding, a human crew would have been safe from radiation on that flight. Objectives added mid-mission. NASA added several test objectives during the flight, taking advantage of opportunities, gathering extra data, valve testing, opening and closing a valve in the pressure control assembly, evaluating whether it affects the slow leak rate in that system. Attitude maneuvers, demonstrating Orion's ability to perform maneuvers at the rate necessary for Artemis II. 3 degree of freedom mode, testing the capability to fly in 3 DOF attitude control mode instead of the typical 6 DOF, proving the spacecraft can operate in a degraded mode if needed. 161 test objectives, all completed, some nominal, some with minor anomalies to investigate, none that would prevent a crewed mission. 20 missions worth of data, collected in 25 days. Nobody there to run the tests manually. The spacecraft did it all, following pre-programmed commands, executing autonomously, reporting back to mission control. Every system validated. Nobody there to celebrate. Flight Day 26, December 11th, 2022. Orion has been in space for 25.5 days. It's traveled over 1.4 million miles, around the moon and back, 2 flybys, 6 days in distant retrograde orbit, 161 test objectives completed. Now it has to come home. The spacecraft is falling toward Earth, accelerating, gravity pulling it in. By the time it reaches the atmosphere, it will be moving at 25,000 miles per hour. Mach 32 times the speed of sound. Faster than any human-rated spacecraft has ever returned from the moon. The heat shield has to handle it. AVSOAT. 186 blocks of ablative thermal protection material, covering the base of the crew module. Each block individually machined and installed. It's an ablative material. That means it's designed to burn off during re-entry. Charring, forming a protective layer, dissipating heat by sacrificing itself. The char layer should be permeable. Gases created by the heat should vent through it, preventing pressure buildup, allowing the material to ablate in a controlled, predictable way. During re-entry, AVSOAT will experience temperatures up to 5,000 degrees Fahrenheit, 2,760 degrees Celsius. Hot enough to melt steel, hot enough to vaporize aluminum. But behind that heat shield, the crew module will stay cool enough for humans. Orion uses a skip re-entry profile. The spacecraft dips into the atmosphere, heats up, decelerates, then skips back out into space like a stone skipping across water. Then it dips in again, more heating, more deceleration, but spread out over a longer time. This reduces peak heating rates, makes the loads more manageable, gives the heat shield more time to ablate gradually instead of all at once, and it makes the G-forces survivable for a cut. It gets set that their age. December 11th, 12:40 p.m. Eastern Standard Time, 1740 Coordinated Universal Time. Orion hits the top of the atmosphere. The plasma starts to form. Ionized air glowing around the spacecraft. Orange and pink and white. Radio blackout begins. No communication with the ground for several minutes. The heat shield does its job. Charring. Ablating. Protecting the crew module behind it. Temperature inside the crew module, comfortable, survivable. And nobody was inside to experience it. Parachute deployment. First, 2 drogue chutes, 15 feet in diameter, deployed at about 25,000 feet, slowing the spacecraft down, stabilizing it. Then, 3 pilot chutes, pulling out the main parachutes, pulling out the main parachutes. Finally, 3 main parachutes, 116 feet in diameter each, fully inflated, like 3 football fields of fabric above the spacecraft. Descent rate about 20 miles per hour, survivable for a crew, gentle enough for the spacecraft to hit the water without damage. 12:40 p.m. Eastern, splashdown, Pacific Ocean, about 100 miles off the coast of Baja California, Mexico. The crew module floats, upright, stable, exactly as designed. USS Portland, a U.S. Navy San Antonio-class amphibious transport dock, moves in. Recovery teams deploy. Small boats surround Orion. Divers enter the water. Orion spent 6 hours in the ocean. Additional data collection. Testing post-splashdown systems, making sure everything still works after the shock of landing. Then the Navy pulled it aboard, secured it, began the journey back to Naval Base San Diego. The crew module came back intact, each shield charred as expected. Parachutes deployed perfectly, all systems functional. Batteries still had power, computers still running, and the crew cabin was still empty. Mike Serafin, Mission Manager, Howard Hu, Orion Program Manager, 25.5 days, 270,000 miles, 161 test objectives completed, every major system validated, nobody aboard, mission success. USS Portland brought Orion back to Naval Base San Diego. From there, NASA transported it to Kennedy Space Center for analysis. Engineers opened the spacecraft, inspected every surface, renewed sensors, downloaded data, examined footage from every camera, and they looked at the heat shield. They expected charring. They expected ablation. They expected the AVCOA to look different than it did before flight. But they found something unexpected. The heat shield had cracked. In over 100 locations. AVSOAT is supposed to char during reentry. It's supposed to form a protective layer. It's supposed to ablate gradually. But on Artemis 1, pieces of charred material broke off. Much larger chunks than Apollo missions experienced. Material loss that was different than predicted. Cracking that wasn't expected. Over 100 locations, some small, some larger, but all indicating that something didn't behave the way it should have, and nobody had been inside when it cracked. NASA launched an investigation. 2 years, nearly 200 AVSOAT samples removed from the heat shield, shipped to Marshall Space Flight Center in Alabama for analysis. Over 100 tests conducted at unique facilities across the country. Thermal protection system experts correlated data, timing of atmospheric descent, sensor readings from hundreds of instruments, imagery and video from multiple cameras. They needed to know what happened, why did it crack, and would it happen again? December 5, 2024, 2 years after splashdown, NASA announced the root cause, the permeability issue. During re-entry, Orion uses a skip profile. It dips into the atmosphere, then skips back out, then dips in again. Each time it dips in, the AVCO8 heats up. Ablation creates gases inside the material. This is normal, expected, part of the design. Those gases are supposed to vent through the char layer, dissipate, escape. But the AVSOAT lacked sufficient permeability. The gases couldn't vent as expected. They got trapped inside the heat shield. Pressure built up, kept building, until it exceeded the material's strength. The AVSOAT cracked. Chunks of charred material broke off and were released. Why did ground testing miss it? NASA performed extensive testing before Artemis 1 ArcJet tests, high-temperature furnaces, simulating re-entry conditions. But those tests used much higher heating rates than the actual flight. At high heating rates, the char forms quickly, ablates quickly. Gas pressure releases normally. Everything behaves as expected. Artemis, the skip re-entry, had less severe heating, lower heating rates, more time between dips. The char formed more slowly, but gases still generated inside the material. Pressure built up faster than the char could form. Gas pressure exceeded material strength. Result, cracking and char loss at lower heating rates than ground tests stimulated. Validation of the hypothesis. Local areas of the heat shield that were more permeable, identified before flight, did not experience cracking or char loss. Those permeable areas allowed gases to vent adequately. No pressure buildup, no cracking, no char loss. This confirmed it. The problem was permeability. The critical finding. Despite the char loss in over 100 locations, despite the cracking, despite the chunks of material breaking off, a human crew would have been safe on that flight. Temperatures within the hull and interior remained within tolerances. The heat shield performed its primary function, protecting the crew module. No penetration to the interior. Significant AVSOAT material remained. The crew module came back intact. No heat damage inside. Temperature stayed survivable. Structure sound. But the investigation revealed a gap in modeling, a flaw in the ground testing approach, a risk that wouldn't have been discovered any other way, a risk that future crews would have faced, unknowingly. And because nobody was on board Artemis I, NASA had time to understand it, time to fix it. NASA had a choice to make. Artemis II, the first crewed Artemis mission, is already assembled. The heat shield is already installed on the crew module. The rocket is stacked in the vehicle assembly building. The launch date is set for March 2026. 4 astronauts assigned: Victor Glover, Christina Koch, Jeremy Hansen, Reed Wiseman. Training, preparing, ready to fly. But the heat shield issue from Artemis I has been identified. The permeability problem is understood. And now NASA has to decide what to do about it. Option 1. Replace the heat shield. Disassemble Orion. Remove the crew module from the service module. Remove the existing heat shield. All 186 blocks of AVCO. Install a new heat shield with the improved formulation. Timeline, months of delay, possibly a year or more. Cost, significant. Schedule impact, Artemis III and beyond, push back further. Option 2, fly with the existing heat shield, then modify the re-entry trajectory. Use the Artemis I heat shield design as is. No hardware changes, but change the skip re-entry profile to prevent the external pressure reduction that caused gas pressure buildup inside the AVCO. Note assembly. Non-replacement. Launch Area 26, December 5th, 2024. NASA announced its decision. Option 2. Fly with the existing heat shield. Modify the trajectory. The rationale. Artemis I proved that a crew would have been safe despite the char loss. Temperatures inside remained survivable. The heat shield protected the crew module. The modified re-entry trajectory eliminates the skip profile condition that caused gas pressure buildup. Different heating rates, different pressure environment. No cracking expected. Future missions. Artemis 3 and beyond will use the improved AVCO formulation with better permeability. The new material is already in development. We'll be ready for those flights. But for Artemis 2, modifying the trajectory is faster, safer, allows the program to proceed without major delays. Some within NASA disagreed. External experts questioned the decision. Was NASA taking unnecessary risk? Should they replace the heat shield anyway, just to be sure? The debate became public. Articles in Scientific American, Space News, Ars Technica, questions from Congress, but NASA leadership stood by the decision, based on data, based on analysis, based on the finding that a crew would have been safe on Artemis I. The value of uncrewed testing. This is why Artemis I flew without a crew. NASA discovered the heat shield issue on a real flight, under real conditions that ground testing didn't replicate. They analyzed it for 2 years, nearly 200 samples, over 100 tests, correlated data from hundreds of sensors. They understood the root cause, permeability, gas pressure buildup, conditions specific to the skip re-entry profile. They developed a fix, modified trajectory for Artemis 2, improved material for Artemis 3 and beyond, all without risking human lives. Other discoveries from Artemis I: electrical system anomalies, latching current limiters switched open without commanding, multiple occurrences throughout the mission. NASA investigated, identified the cause, developed fixes for Artemis 2. Mobile launcher damage. The launch pad sustained more damage than expected from 8.8 million pounds of thrust. Concrete cracked, deflector plates bent. Repairs and upgrades needed before Artemis II could launch. Navigation system validation. Real-world performance data informed operational constraints. Engineers now know exactly how the system behaves at lunar distances, can plan trajectories with confidence. Radiation data from Helga, Zohar, and Commander Munikin Campos, validating crew safety for deep space missions beyond Earth's magnetic field, all discovered because nobody was on board. Apollo comparison. Before Apollo 11 landed humans on the Moon in July 1969, NASA flew multiple unscrewed tests. Apollo 4, November 1967, unscrewed test of Saturn V and Command Service Module. Apollo 5, January 1968, unscrewed test of Lunar Module. Apollo 5, January 1968, unscrewed test of Lunar Module. Apollo 6, April 1968, second unscrewed test of Saturn V, then Apollo Cabal. Modern NASA has lower risk tolerance. Better technology allows more thorough uncrewed testing. Sensors that didn't exist in the 60s. Computer simulations, real-time telemetry from 250,000 miles away. Artemis I was more comprehensive than Apollo 4, 5, and 6 combined. 161 test objectives, 25.5 days. Full mission profile from launch to splashdown. The philosophy: test it, find the problems, fix them, before putting 4 people on board. That was the plan all along. They learned what they needed to learn without losing anyone. 25.5 days, 161 test objectives, 270,000 miles from Earth. Records broken. Farthest distance from Earth for a human-rated spacecraft, 268,563 miles. Broke Apollo 13's 52-year record. Fastest re-entry velocity from the Moon, 25,000 miles per hour, Mach 32. Longest mission for a spacecraft designed for human deep space exploration without docking to a station. 25.5 days. First integrated flight of Space Launch System in Orion. First launch from Kennedy LC-39B since 2009. Most powerful rocket launch since Saturn V. Systems validated. Space Launch System. 8.8 million pounds of thrust, 322 feet tall. Performed within 7 feet per second of target velocity. Remarkable precision. Orion spacecraft. Propulsion. Navigation. Communications. Thermal control. Life support. Everything worked. European service module. Provided power, propulsion, water, thermal control, atmosphere for 25 days. Solar arrays generated 15% more power than projected. Heat shield. Protected the crew module despite unexpected char loss. Temperatures inside remained survivable. Function, protecting crew missile. Result, success. Problems discovered. Heat shield permeability issue. Over 100 locations with char loss. Root cause identified after 2 years of analysis. Solution, modified trajectory for Artemis II. Improved material for Artemis III and beyond. Electrical system anomalies. Latching current limiters switching open unexpectedly. Investigated. Fixed. Mobile launcher damage. Launchpad repairs and upgrades in progress. Navigation, radiation, operations data, all gathered, all analyzed, all informing future missions, all found, all analyzed, all addressed before crew. Why it mattered. This was the dress rehearsal, the full end-to-end test before the real show. NASA needed to know if the system worked, not theoretically, not in simulations, not in ground tests that might miss critical conditions. In reality, under real flight conditions, real heating rates, real trajectories, real space environment. They needed to know what they didn't know, and they found out. The spacecraft was designed for 4 people, life support for 3 weeks, seats with a view. Windows looking out at Earth and Moon, controls for manual flight if needed. A view of the Moon from 80 miles up, a view of Earth from 270,000 miles away, a view of Earth from 270,000 miles away, a view of the cosmos that only 24 humans have ever seen. And nobody was there to see it. That was the point. Because when NASA sends 4 people around the Moon in March 2026, they'll know the spacecraft works. They'll know the systems are validated. They'll know the heat shield will hold with the modified trajectory. They'll know the propulsion is accurate. They'll know the propulsion is accurate. They'll know the navigation is reliable. They'll know the life support will keep them alive. They'll know because Artemis I proved it. The dress rehearsal is over. Next time, there will be 4 people on board. Victor Glover, NASA astronaut, pilot, the first black astronaut to fly beyond low Earth orbit, the first person of color to leave Earth's immediate neighborhood. Christina Koch, NASA astronaut, mission specialist, the first woman beyond low Earth orbit, holds the record for longest single spaceflight by a woman, 328 days on the International Space Station. Jeremy Hansen, Canadian Space Agency astronaut, mission specialist, the first non-American to fly beyond low Earth orbit, representing Canada and the international partnership that makes Artemis possible. Reed Wiseman, NASA astronaut, commander, leading the crew, responsible for 4 lives on a 10-day mission around the Moon. 4 astronauts, 4 firsts, the first crew to fly beyond low Earth orbit in over 50 years. Vivers Dokub. 10 days around the Moon. No landing, just like Apollo 8 in December 1968. A test, a validation, a confirmation that humans can survive the journey. And then Artemis III, the landing, the South Pole, boots on the lunar surface for the first time since 1972. The ship came back empty. Next time it won't be. This is Stardrift FM. Keep drifting.